Let's talk about biostratigraphy. Biostratigraphy, yeah, that's pretty good. So, stratigraphy is the geology term for sort of separating out all the big sedimentary rocks into layers, which will basically be like separating out a mountain into time intervals effectively. Biostratigraphy specifically is when you use fossils to do that. So if you've got multiple formations and they have the same fossil in there, and that fossil doesn't occur below or above, a particular formation, then it is probably coming from about the same time. And if you can find several different types of fossils that are all correlated, and you find the whole like ecosystem here, and then you find the at this other spot, chances are, yeah, you're looking at the same time roughly, same sort of window of time. So, how do we do this? What do we use? Yeah, how do smart scientists figure this stuff out? In the old days, the ideal was that you should have hand specimens, something you can hold in your hand and it'll sit on your palm and it's just the right size. Here's a gross tissue. There we go. And you can look at it and identify it without a magnifying glass and just say, I know exactly when we are. And there you go. That works really well for ammonites in parts of the Mesozoic in Europe. It does not work so well for the Paleozoic, which is longer, and uh, generally, I don't know. I don't know that it's particularly useful, but hey, it's great when it happens. What are things that people actually use? Well, look at these little guys. So these are little microscopic fossils, and you're going to get these. These are rhizaria. So these are radiolarians. They're going to be part of the group of SAR, alveolates, straminopeles, and rhizaria. These things that are eukaryotes and have all kinds of crazy biology, weird combinations of things, but they're definitely not plants or fungus or animals. They are all the other branches of other stuff. Things that are both photosynthetic and have eyes and can move around, little weird things like that. Um, and so these are the skeletons of some of those. And you can identify, like, oh, okay, when does this one come in? When does it first appear? When does it last appear? And there we are, matched up against the timeline. And so if you find a particular one, there are some that are only found in a single period, and there are others that run a little bit broader range. And so if you can find a couple of these, then you can tell pretty well exactly when you are in time. So that's neat. So those are radiolarians, radiolaria, yeah. These are much more widely used. These are called conodonts, or rather, these are called conodont elements. The conodont animal looks sort of like an eel with no jaw, but with a bunch of little teeth embedded down in its throat. And these are some of those teeth. And they change really rapidly over time, and these things are globally distributed, so they're really useful. You'll get members of the same genus, like Neonathodus, and they will just be popping up in Russia and Eastern Europe, and also in the Americas. So, pretty helpful. And so it's these teeth. And so we're going to measure. There's like a right and a left version of these, but just sort of mirror it in your mind. You're going to be looking at, all right, what's the grinding surface look like? What does this sort of, whatever this is, maybe this is the grinding surface. Maybe this is like a crushing surface back here. What's the overall shape of it? How long an extension does it have on the back? What are the relative proportions of these things? And this is a skill, or this has been a valuable skill. People who can identify all the microfossils that might come up in like a core section have been, historically at least, very valuable in, for example, gas and oil industry. They will sink down a big long sort of cylinder. They will take out all the rock in that cylinder. So you'll have hundreds of feet of rock, but a little cylinder of it, crack it open at different points, and anywhere that you find these tiny little fossils, you can date it. And so you can tell exactly when you are, and then they'll know that, oh yeah, on top of this particular rock, we expect there to be a nice little oil reserve, and you'll see the oil dripping out of the core section, if it's any good at all. And if it's not, then at least you know when you are. So useful to geologists, useful economically as well, at least historically. And those are conodont elements. Conodont. Conodont. Yeah. Cone-shaped tooth. They're not really cone-shaped, but I guess they got little cone-shaped bumps on the back here. But they are tooth-like. Yeah. Okay. Shown here. These are bivalves. For a long time, people thought there's no way you can use bivalves for biostratigraphy because they're too hard to identify, or they're not very well characterized. We don't know when each one of these things tends to sit, but then somebody went and did it. They just went and did it. And so this time that I picked out happens to be the same branch of time that we'll be studying here in Texas. So if you ever run across any of these particular things, you will know roughly when you are. Now, there are a couple very common genera and species that you'll find across most of this range, and so those are not going to be particularly helpful, except to say that you're in a wide swath of time. But yeah, if you can get somebody dedicated enough to study it, basically any fossil, body fossil, even ichthyofossil, can be a biostratigraphy marker. Why not do it with insect wings? Why not do it with insect wings? To do this, they're actually going to look at the pattern, the sort of venation, the little veins in the wings, and they are different and they are distinct. And you can describe these, which is exactly what people do. And so anywhere that you get insect fossils, you will be able to, even if you only get wings, which sometimes preserve better than whole bodies, you'll still be able to identify exactly when you are in time, which is pretty awesome. Because in some environments, like if you're in a marine environment, you're going to have conodonts probably. And so it's going to be okay. You don't need to go to these other ones. If you're in a marine environment where conodonts didn't exist, but you had little microscopic guys, then maybe radiolarian is going to be good. What if you're too close to shore and the conodonts and the radiolarians would just get destroyed or could not live there? Well, you may get some of these clams because clams are robust. And so, yeah, bivalves may be the biostratigraphy choice for you. Yeah. What if you're in a coal swamp, though? That's not going to be marine. And so all those other things live in salt water. And so if you're falling down into swamp mud in the Carboniferous bayou, then you're not going to be able to, use these marine markers. You're going to need something sort of swampy, like insects. The world is full of bugs around this time. They leave lots of wings. And so it's not the easiest way to do biostratigraphy, but it may be the only way for a particular type of fossil, like a particular fossil bed. Yeah. Can you do it with vertebrate fossils? You sure can, yeah. Are you ever going to find like more than one complete enough vertebrate fossil in your lifetime to be able to do this? Unlikely, unless you go into that and then maybe you find like 2 or 3. But the important point is that they could be biostratigraphy markers. And the interesting thing here is you got a lot of bones. So even if these things fragment and go just all willy-nilly, if you have a particular bone or a set of bones, like 2 or 3, and they are distinctive enough, then you can still potentially identify what time it is. Because that's the question with biostratigraphy. What time is it right now? Can you do it with ichthyofossils? Of course you can do it with ichthyofossils, because ichthyofossils are made by animals mostly, and I guess some plants, yeah, but not very many plants. And animals definitely evolve from time to time. And so here we're doing it with footprints, and there are particular characteristic footprints. Now, we wouldn't always know what kind of animal actually even made these footprints. We may have the prints, but not the animal, if it didn't happen to fall into the right bog and get formed into a body fossil. But that's okay because we can still tell what time it is. And that's the main goal of biostratigraphy. Can you use plants? I don't know. Yeah, sure. Yeah. The plants are kind of outside the focus of this class because we're talking about animal evolution, but of course you can use plants. You have to learn how to recognize them. You got to learn what they are first. But yeah, definitely. It's a possibility. One of the favorite things that I have seen actual biostratigraphers do, they love their conodonts, but they also really like these things. So these are called fusolinids. They're fossil foraminifera, so little eukaryotic cells, probably single cells. And they have these awesome looking, very intricate little tests, like a little protective case that they grow around themselves, and they sort of continue to make larger. They'll just keep expanding it. You can slice these open, and they look really different inside and can be quite distinctive if you know how to read these. So here are some of the ones from this part of Texas at the Des Moines and Missourian boundary in the Brazos River Valley. Yeah, which is the Brazos River a bit north of here, but yeah, you get it. Same river. So, what are the principles of biostratigraphy? That for every time there was a set of organisms, and if you find the same organisms, you're probably dealing with the same time. And so, if you can identify the organism precisely, and then you can probably say that it's the same time as somewhere else that you identified the organism. So you can do what is called relative dating. You can say these are both in the biozone that has this particular fossil. You name it this particular fossil biozone. And later on, people can do other tests like geochemistry, and they can maybe try to figure out exactly when those are in actual time with some of those isotopic dating techniques. What makes a useful biostratigraphic indicator species? Well, it's super useful if it has a wide distribution, so you can find it in different places, because the whole point of biostratigraphy is to correlate time between different places, so you know that you're looking at the same time roughly. You'd also love for it to be sort of common so that you can actually find it at those sites if it's there. But as we saw with the skulls, perfect vertebrate skulls chart, yeah, practicality need not concern you necessarily. We're scientists here. What type of fossils are most commonly used? I mean, the most commons are going to be conodont elements and fusolinids. And everything else is secondary, but you do get a tendency, like the smaller the fossil, the more likely it is to be widely used as a biostratigraphy marker. Just because you're more likely to hit one of those in a core sample as you're going through, and so that's why people put in the time to actually figure out when each of those are from. Okay, give some examples of fossils used for biostratigraphy. Oh my gosh, that's what this whole little mini lecture was. So, hey, flip back, have a look through, get some examples. I bet you can find several. All right, thanks very much.